Swayam Prabha. Digital India. Educated India.
Hello everyone, welcome to this course on gas turbines and jet engines. So, today is lecture 14 of this course. So, this is the fourth lecture of week 3 and today we are going to learn the final ideal cycle for gas turbines, which is the combined intercooling, regeneration and reheating cycle. So, till now we have seen various combinations or standalone cycles with intercooling, with regeneration or with reheating. Now, if all three are combined, then also a gas turbine cycle is possible and we will see that it has the best performance characteristics. So, we are going to analyze this cycle and see its performance characteristic, okay. And then we are going to solve numerical problem on this intercool regeneration reheat combined cycle. Okay. So, the concepts cover are analysis of this combined cycle and problem solving for this combined cycle. Okay. So, till now in the last class we have seen what is a combined intercooling and reheating cycle. Okay. So, it combines both dividing the compression process into two parts by adding an intercooler in between and dividing the combustion process, the expansion in the turbine in two parts by adding a reheating or secondary combustion in between. Okay. Now, if you remember, if I draw the TS diagram, first we will draw for reheat intercooled reheat cycle and then we will modify that for addition of regeneration also. Okay. So, we had these processes, by this time it should be clear to all of you, 1 to 2 low pressure compression, 2 to 3 intercooling, 3 to 4 high pressure compression, okay. Then 4 to 5 primary combustion, the main combustion, then 5 to 6 expansion in the high pressure turbine, 6 to 7 is secondary combustion or reheating, and then from 7 to 8 we have the low pressure turbine expansion, and then we had closed the cycle by adding the hypothetical cooling process, heat removal process going from 8 to 1, the constant pressure heat removal. So, this was the cycle in our previous class we have studied for combined intercooling and reheating. Now, what we can see from here is that the temperature at the exit of the high pressure compressor. So, at the exit state 4 is at a very low temperature compared to the temperature at the exit of the low pressure turbine, which is at state 8. Okay. And for ideal cases with optimum conditions, we have also noted that T 6 equal to T 8 and T 2 equal to T 4. So, this temperature difference is very large, okay, which is good because now if we add a regenerator, we have a large scope of regeneration, because the temperature difference is so large, there can be significant considerable heat transfer from the combustion products at state 8 to the air at state 4. Okay. So, which means that if we add a regenerator, there is a distinct possibility that the efficiency of the cycle is going to increase by quite a big margin. Okay. So, with that idea regeneration is added, and this regeneration part goes from 4 to let us say 9. Okay. From 4 to 9 is the regeneration in the air side. So, the air gets heated up to state 9. So, we are assuming that effectiveness equal to 1, regenerator effectiveness equal to 1, and of course, optimum conditions, optimum intercooling and reheating. Optimum intercooling and reheating. Okay. So, the corresponding heat transfer will occur from this state 8 and we will reach temperature equal to T2. So, let us call this state as state 10. So, from 8 to 10 is the heat transfer in the regenerator from the combustion products. Okay. So, then from 10 to 1 we have the additional heat removal process to the external say low temperature reservoir, which we have added this hypothetical process for closing the loop, as we have already discussed several times. Okay. So, we can see that by adding this regeneration now, because the regeneration can lead to this much of considerable heat addition, the actual heat addition from external source like this in the combustion chamber is considerably reduced. Okay. It is drastically reduced, and so it means that the requirement of fuel or the energy requirement is drastically reduced in this case. The work output remains same as the previous cycle, reheat and intercool cycle, because there is no change to the turbine work output or compressor work input when we are adding regenerator, but because the heat input overall decreases by such a large margin, we expect that the efficiency is also going to be very high. So, this is a very effective combination, although it has practical difficulties because you are adding all the components. So, it becomes a very bulky system. Okay. So, before analyzing this, we will just have a quick look at the component arrangement. Okay. So, state 1 is the inlet, this is state 1, let me use some other color, let us use green. So, this is the inlet state 1. So, from 1 to 2 is the first compression going from here to here. So, this is 2, then we have the intercooler or intercooling process from 2 to 3. Okay. So, from 2 to 3. So, this is state 3, then the second compression process going for 3 to 4. Okay. Then from, so here the way it is nomenclature is used, 4 to 5 is the regeneration. So, in our case we are naming this as 9, okay, state 9. So, going from 4 to 9 and from 9 to 5 is the first combustion process. Okay. So, from here and here, then we have the expansion in the high pressure turbine going from 5 to 6. Okay. So, going from 5 to 6 and from 6 to 7, again our numbering is different from that of the image which is taken from the book of El Sayed Ahmed, but it does not matter. So, from 6 to 7 we have the second combustion, and from 7 to 8 we have the low pressure turbine expansion, and then from 8 to 10 we have this process which is the other side of the regeneration process from where the heat transfer occurs. Okay, and the exhaust gases go out at state 10, but in our cases we are closing the cycle by connecting 10 to 1 by using a additional heat removal process. Okay. I hope this is clear, otherwise you can pause here for a little while and just try to understand this in more depth, okay, and try to correlate with the cycle TS diagram. So, analysis is not much different from all the previous cases, particularly it is almost similar to the reheat and intercool combined cycle. Okay. So, in this case the work input, let us go back to our previous color. In this case the work input and work output remains same. So, the net work also remains same. Okay. So, which we had found to be equal to. So, W net by CPT1 we had derived an expression, and for combined reheat regenerative cycle, let us come back to this. So, we had found that this is equal to 2 T minus T by root C minus root C minus 1 within brackets. Okay. So, same will be the case for this combination of all the three phenomena. Okay. Now, for the efficiency, of course, we know that there will be variation because the heat addition actually varies. So, this is equal to W net by net heat addition, which is the combination of both the combustion processes. So, this is equal to CPT1 multiplied by 2 T minus T by root C minus. So, there will be a 2 here which I have missed. Okay. So, this will be minus 2 root C minus 1, root C minus 1. Later you can compare with that of the reheat. So, it should be same, okay, if there are no errors. Heat addition in this case is very simple. So, it is from 9 to 5, okay, this process, and from 6 to 7. Both are equal because as per our conditions T 5 is equal to T 7, and we have defined that for 100% effective regeneration T 9 is equal to T 6. Okay. So, T 5 minus T 9 equal to T 7 minus T 6. Okay. So, we can write this as C P T 1 T 5 by T 1 minus T 9 by T 1 plus C P T 1, although it is the same we are writing because we want to know what is the exact expression, T 7 minus T 6. So, T 7 minus T 7 by T 1 because we have taken out T 1 outside the bracket minus T 6 by T 1. Okay. So, C P T 1 can be cancelled, which gives us the formula, not formula. So, I have already been repeating that we should not call this as formula, but the expression that we have derived. So, we have derived this expression W net by Q in. So, this is equal to 2 T minus T by root C minus 2 root C minus 1. Okay. Then what is T 5 by T 1? T 5 by T 1 is T. Remember that we had derived that T 5 by T 1 is, by definition this is equal to T. And what is T 9 by T 1? T 9 by T 1, okay. On the right hand side let us do rough calculation. So, T 9 by T 1 is equal to T 9 by T 5 into T 5 by T 1. Let us go back and see what it means. T 9 by T 1 is equal to T 9 by T 5. Okay. So, 5 and 9 are related, right, because T 9 is equal to T 6. So, we know the relation between 5 and 6, and T 5 by T 1 are also related. So, this T 9 by T 5 can be written as T 6 by T 5, and this is small t. Okay. Now, what is T 6 by T 5? T 6 by T 5 is 1 by root C. Previously, we have established that. So, 1 by root C So, this is T by root C. Okay. So, this Q in is then T minus T by root C. The second term also will yield the same value, because T 7 and T 5 are equal, T 6 and T 9 are equal. Okay. So, we have 2 times of this, which then gives us. So, in this case finally some simplification is possible to the expression, which is luckily which is possible. So, the first term will become 1 and then 2 and 2 gets cancelled, minus root C minus 1. Okay. If I take a root C common, okay, so we are left with 1 minus 1 by root C. Okay. So, this becomes equal to root C by T, rest of the terms get cancelled. So, finally, we are left with an expression for efficiency, which is of the simple form, although cycle is the most complex cycle. Because of cancellation of the terms, we are left with dependence of efficiency on R, pressure ratio, and the temperature ratio T as 1 minus R to the power gamma minus 1 by gamma root of that divided by T. So, R to the power gamma minus 1 by gamma has been defined as C for us. So, it means that eta equal to 1 minus root C by T. Okay. So, accordingly we can plot the values of efficiency and we can see what is the effect of C and T. Okay. For example, the limiting value for C equal to 1, this becomes equal to 1 minus 1 by T, which is the same as for the regeneration cycle, only regeneration. Actually, it is same for all the regeneration cycles, for as we will see in the next class when we will do a quantitative comparison. For all the regeneration cycles, the limiting value at R equal to 1 becomes equal and is equal to 1 minus 1 by T. Okay. So, let us draw the performance characteristics. Here we will draw qualitatively, so that we can have a quick comparison, qualitative comparison. Later we will have a full quantitative comparison. So, we are not drawing the net work output by versus R curves, because the work output remains same as the previous cycle, which is the combined intercooling and reheat cycle. So, in this case we need not draw it again, but for efficiency versus R we can compare it. So, this is let us say the minimum value correspond of R corresponding to 1, okay, and we will draw this line which shows the limit of minimum value of R. So, now for standard Brayton cycle we know that standard Brayton cycle keeps on increasing the efficiency at a slower and slower rate. So, this is standard Brayton and it does not depend on T at all. So, it only depends on R. And for normal regeneration, okay, we had found that, or let us say that the highest efficiency that we had found till now is intercooling plus regeneration. So, for intercooling plus regeneration we had obtained efficiencies like this. So, this is causing issue. Or let us continue this, because still exists, although it goes below that of standard cycle. So, for different values of T it would be like this, right. So, with increasing T, again let us see this. So, with increasing T we get something like this. Let us say this is T equal to 5, T equal to 4. Of course, it will not go to 0, this is T equal to 3. So, for so this is, let us say this is intercooling plus regeneration, which is the highest efficiency we have obtained till now. Slightly higher than that of reheat plus regeneration. Now, for this case, combining everything together, we get the highest efficiency, okay, highest possible efficiency among all cycles. So, it is even beyond that of the intercool plus reheat cycle. Okay. So, let us draw it using some other color. So, it will decrease very gradually. Still the pattern is similar, it keeps on decreasing, but the decrease occurs very gradually. Something like this. So, this will be t equal to 5, t equal to 4. So, this becomes even flatter actually, the way I have drawn it looks like it is decreasing significantly, but it decreases very slowly, as we will see in the next class. Okay, maybe we can draw this with another color, so that it is more widely visible. So that it is more easily visible. So, it will keep on decreasing very slowly like this. T equal to 5, t equal to 4 and t equal to 3 for this case. So, highest efficiency and work output is of course also highest, because it is same as the work output for that of reheat plus intercooling cycle, which already had the highest work output. So, both highest work output as well as highest efficiency is obtained in this cycle. I have not drawn the combined reheat and intercool cycle, because in those cases the efficiency curves are different, because there is no regeneration, the efficiency keeps on increasing, but you know that efficiency is drastically lower in those cases when there is no regeneration. Okay. So, this regeneration when added to intercooling and reheating is extremely effective, because we had discussed that the scope for regeneration, this delta T is now extremely large, okay, extremely high. Okay. As a result, this is the most effective cycle. So, although this becomes very bulky, so there are some drawbacks, that this has all the different components. We have a bulky intercooler, then we have 2 combustion processes, combustion chambers, 2 turbines, 2 compressors, then regenerator, which is again another large heat exchanger. So, it becomes bulky, but for industrial gas turbines, for power generation, where mobility is not of concern, okay, and it is installed at a fixed location, in those cases we can get very high performance characteristics by using all this together. Okay. So, for other applications where weight is of high importance, like aerospace applications, in those cases of course, these modifications are not important. There we will study later, the modifications are closely related to that of simple Brayton cycle. Okay. So, we will finish this with an example of a combined intercooled regenerative reheat problem. Okay. So, a cycle problem which combines all 3, and for this we will take the same problem profile. So, same problem setting, same design parameters, ambient temperature of 300 Kelvin, initial the pressure ratio, overall pressure ratio is 10, and the maximum temperature or turbine inlet temperature is 1500. Same problem we had done with same conditions in the previous classes also. So, for example, I have shown here the previously solved problem, which we have done in the previous class for the combined intercooled reheat cycle. Okay. So, because most of the properties will remain same, or the even the state values in our case, except that we will now have a regeneration here going from 4 to. So, we will have a regeneration going from 4 to this point, which we will call as 9, and another the equivalent cooling here from 8 to 10. Okay. So, all these states will be same as this, and T 9 will be equal to T 6 equal to T 8, which we already know T 6 and T 8. Similarly, T 10 will be equal to T 4 equal to T 2, again we already know this. So, all these states will be similar to this. Okay. So, based on this, okay, we will directly obtain the values whatever is known to us, we will directly write down. Okay, let us, or we can use this example itself as the template for the final problem. We can keep this. I am directly writing here that this is for regenerative. So, so as to save time, because we are going to do the same problem again. Okay. So, I do not want to waste time. So, now we have this additional processes going from 9 to 10, 4 to 9 and 8 to 10. Okay. All the temperature values are as obtained. The only issues, only problem changes that will occur are that the heat addition is going to change. Okay. So, probably this cannot be, let me see, the entire thing is erased. Okay. So, better I think it is will write in the next page. Okay. We already have these temperature values. The only change that will occur is that the Q in will become different. So, what will be the value of Q in? I am not writing the entire thing again. So, W net will remain same as we already know 610.28. So, Q n now will be 2 into C p T 5 minus T 9. And what is the value of T 9? T 9 and T 10, those are the additional states for this cycle. So, T 9 is equal to T 6 and we had obtained T 6. We have obtained T 6 as 1079.53 and T 5 of course is equal to 1500 Kelvin. Okay. So, 2 times this. So, this is equal to 845.14 kilojoule per kg for this combined intercooled reheat regenerative cycle. So, you can notice how much the heat transfer had reduced from the by the addition of regeneration. Without regeneration, we had a value of 1511.14. So, 1511.14 and it has decreased drastically to a value of 845.14 just because we have added the regeneration. The regeneration is so powerful here. Okay. And as a result, the efficiency is also going to change. So, in this case instead of 0.404, we will get a very high efficiency, as you can see 610.28 divided by 845.14. So, this is equal to 0.722, okay, 72.2%, which is remarkably high value if we consider a heat engine operating between these temperatures. So, this is a very high value and this is only possible because of the combination of all the three phenomena together. Okay. This is much higher as compared to all the other previous values that we had obtained, and the work output is also highest, but is still equal to that of the combined intercooled reheat cycle. So, if we put the values here, the final values, we can compare. So, this case the work remains same 610.28, whereas the efficiency increases dramatically to 72.2%. Okay. So, this is from our latest calculation. All these are from the hand calculations that we have done. So, we have solved each of these problems with the same setup, so that we can have a very nice and fair comparison, and we see that the intercooled plus regeneration plus reheat cycle has the highest work output, and it has a remarkably high efficiency, which is 72.2% for these parameters, and it reduces very slowly if we go to higher value of R, okay. And it is considerably higher than the next highest value. Next highest values are for intercooling and regeneration, which is 67.7%, and regeneration and reheat, which is 66.8%. So, you can pause here and you can see what type of percentage increase or decrease occurs when each of the phenomena is changed in both the work output and the efficiency. You can try to calculate and get a very good feel about the numbers which are involved, because we have taken practical values in this problem, all these problems. You will get a feel for practical numbers which are involved. Just one final comment here is that, like I have already mentioned many times, these efficiencies are for the ideal cycle. That is why these numbers are very high. In practical application, we will not be able to achieve this high efficiency, because there will be losses, but efficiency beyond 50% is possible, and even larger efficiencies have been reported in recent years for these combined cycles, going up to 60%. Okay. So, now we conclude this. So, this actually completes the individual discussion of all these ideal gas turbine cycles. So, we have analyzed the final cycle, which combines all the three important processes: intercooling, regeneration and reheating, and we have solved a problem based on the same framework and same setup. So, same design parameter values. We have obtained the performance characteristics or performance parameter values, efficiency and work output for this combined intercooled regeneration reheat cycle. Okay. So, these are the references. So, with this we complete today's class. Thank you.